We will now hear testimony from Mr. Roy Thomas, a senior principal engineer with the American Bureau of Shipping, ABS. Mr. Thomas, I see that you have counsel present here in the courtroom. Counselor, can you please identify yourself?
Good morning, Captain Neubauer. Gerard White, Hill Rifkins, LLP, outside counsel for the American Bureau of Shipping.
Thank you. Mr. Thomas, the recorder for this proceeding will now administer the oath.
You raise your right hand for me, sir. A false statement given to an agency of the United States is punishable by a fine and/or imprisonment under 18 U.S.C. 1001. Knowing this, do you solemnly swear that the testimony that you are about to provide will be the truth, the whole truth, and nothing but the truth, so help you God? Thank you. You may be seated.
Mr. Thomas, thanks again for coming today. I'm going to pass the questioning to Commander Whalen.
Good morning, Mr. Thomas, and thank you for being here with us today. All of our questions are going to be related to your background and experience as a principal surveyor for the American Bureau of Shipping and any interactions that you may have had with OceanGate. Before we begin, I'm going to ask you to please refrain from using any acronyms. If you should use an acronym, I'll stop and have you tell me exactly what that acronym means. And we understand that you have provided or brought with you a presentation, and that presentation will be brought into the record as Exhibit 104 after the hearing, or after today's hearing. Before we get into that exhibit, can you please provide to me a little bit more about your background in both education and relevant work history?
Absolutely. So I have a master's degree in ocean engineering and naval architecture with a specialization in underwater vehicles from Memorial University of Newfoundland, Canada. And I have a bachelor's degree in marine engineering from Marine Engineering and Research Institute, India. So I joined ABS back in 2003 as an engineer with a machinery group working out of the Houston office. And I started with a planned review of manned submersibles, diving systems, other underwater units, and then cranes, cargo gear, pressure vessels, boilers, Type C LNG tanks, and other pressurized equipment. Okay. So then over the years, I worked my way up from engineer to senior engineer. Then I was a principal engineer. And then I became managing principal of the underwater systems and lifting appliances group. Okay. So over the years, I worked as a lead plan review engineer for the review of numerous submersibles. So these included the Octosub or the Pagu submersible. This was built by International Submarine Engineering and was owned by Paul Allen, who was a co-founder of Microsoft. Then I worked on various new construction submersibles built by Titan Submarines out of Florida and Seamagine Hydrospace out of California. Then I was a lead engineer for the design review of the pressure hull of the Alvin submersible. So they built a new pressure hull that was rated for 6,500 meters seawater depth or 21,000 feet seawater depth. So I was a lead engineer for that. And then I was a lead engineer for the design review of the pressure hull and transfer skirt, as well as the launch and recovery system for the U.S. Navy's submarine rescue diving and recompression system. And I also worked on modifications for various existing submersibles. So I worked on the Pisces submersibles that were built out of Canada from International Hydrodynamics. Then I worked on the Perry series of submersibles that were built by the Perry submarine builders in Florida. So they had the PC series of submersibles that were built in the late 50s and 60s and 70s. And then I also worked on the deep rover submersibles and various other submersibles. So apart from manned submersibles, I also worked on manned diving systems. So I worked on saturation diving systems, air diving systems, mixed gas diving systems. And these include diving systems built by Oceaneering, as well as various other companies such as Aqua Air, and diving systems built by DRAS out of Italy. Okay, so these are all examples of some of the systems I've worked on. So over the last 20 years, I've also served as the coordinator and moderator for the annual meetings of the ABS Special Committee on Underwater Systems and Vehicles. So this special committee includes experts from around the world. And one of the functions of this committee is to review proposed rule changes to the ABS underwater rules. So when we propose changes to the rules, it's circulated to these committee members, and they are experts in the underwater field. So they have a look at the proposed rule changes, they give us their feedback and their comments, and then we address these comments. Then I've also played an active role in the last 2 decades in updating the ABS underwater rules. And I've drafted various new chapters in the underwater rules. So I authored the new chapters on ambient pressure submersibles, diver lockout submersibles, diving systems, atmospheric diving suits, hyperbaric facilities, undersea habitats, remotely operated vehicles, as well as autonomous underwater vehicles. So all of these are chapters that I authored in the last 2 decades. Now, for the last 14 years, I've also served as an instructor for the 2-day submersible training course conducted by the ABS Academy. So this training course gives an in-depth look at the ABS rule requirements for submersibles, and we also look at the lessons learned from various submersible and submarine accidents over the years. Okay. Now, apart from my regular work responsibilities, I also serve as the chair of the ASME PVHO subcommittee on submersibles as well as diving systems. So ASME stands for American Society of Mechanical Engineers, and PVHO stands for Pressure Vessels for Human Occupancy. So this ASME PVHO standard is one of the leading international standards for pressure vessels for human occupancy. It's widely used in the United States as well as around the world. And the applications it addresses are medical hyperbaric chambers that are used in hospitals. It addresses manned submersibles and also addresses diving systems. Then I also serve as the chair of the SNAME Technology and Research Panel OC6. So SNAME stands for Society of Naval Architects and Marine Engineers. So this panel is currently working on updating the SNAME textbook, Submersible Vehicle Systems Design. So this is a reference that is widely used by submersible builders and designers, as well as graduate students at universities worldwide. And then over the last 9 years, I've also served as a representative of the International Association of Class Societies, or IACS, at working group meetings at the International Maritime Organization in London. Okay? So from 2020 to 2023, I served as the IACS representative on the experts group for diving systems. So this experts group developed the IMO diving code, the 2023 IMO diving code, which is currently in force and is used around the world. Then from 2014 to 2022, I served as the IACS representative on the IMO working group for lifting appliances and anchor handling winches. So this working group developed amendments to the IMO SOLAS Convention, that's a Safety of Life at Sea Convention, as well as they prepared guidelines for lifting appliances and anchor handling winches. So these SOLAS amendments and guidelines will come into force from 1st January 2026, and they require certification of lifting appliances and anchor handling winches that are installed on ships. Okay? So that is a brief summary of my educational as well as work experience.
Thank you, sir. Did the American Bureau of Shipping, or ABS, perform any services for OceanGate in support of the Titan Submersible?
No, we didn't perform any services for the Titan Submersible, and they didn't reach out to us with a request for class or request for any services.
You had mentioned IACS, or the International Association of Classification Societies. Of the societies, what societies do classify submersibles?
So apart from ABS, I'm aware that DNV classifies submersibles. We have Lloyd's Register and RENA. So these are the leading societies that class submersibles.
So just to clarify, so DNV and Lloyd's Register are two separate?
Correct. They are two separate organizations. So DNV is based out of Norway. Lloyd's Register is based out of the United Kingdom.
Thank you, sir. If at this time, if the recorder can please bring up Mr. Thomas's, go ahead, sir.
Sir, I think you mentioned RENA also. Can you define that, sir?
So that's an Italian class society based out of Italy. It's a complex name, Registraro Navale Italian or something. So I'm not sure of the exact.
Yes, sir. I just wanted to make sure there
Yes.
was one other that you
Yes.
mentioned.
Thank you, sir. Mr. Thomas, if it's at this time, if you want to go through your presentation?
Yes, absolutely. Okay, so I have a presentation which covers pressure hull requirements for passenger submersibles. Okay, next slide. So this presentation basically looks at classification and class societies. We look at the ABS experience with underwater units. We'll briefly look at the submersible rules, regulations, and standards. And we'll also address a few questions on carbon fiber pressure hulls. Next slide. Next. Yeah. Okay, so what are class societies? So class societies are organizations that publish rules for the classification of ships, offshore facilities, and other marine vehicles such as submersibles. Then they conduct design review and surveys to check for compliance with the rules. And class societies also issue class certificates and maintain a register or a database of ships, offshore facilities, and other marine vehicles that the society has classed. So at present, there are more than 50 organizations around the world that offer classification services. Now, out of these 50, 12 class societies, including the American Bureau of Shipping, are members of the International Association of Class Societies, or IACS. So IACS's mission is to develop minimum technical requirements for the design, construction, maintenance, and survey of ships and marine-related facilities. And IACS also works to assist international regulatory bodies such as the International Maritime Organization and standards organizations to develop and interpret statutory regulations and industry standards. So IACS member societies are typically well-established class societies that are recognized by flag administrations around the world. At present, IACS member societies are responsible for classing around 90% of the world's maritime tonnage. Next slide. So in most countries, by law, only classification societies can class submersibles, ships, and offshore facilities. And the role of classification has been recognized by the International Maritime Organization, or IMO, in the Safety of Life at Sea Convention, as well as other international conventions. So class societies act as recognized organizations, performing statutory inspections, as well as design review on behalf of flag administrations. Next slide. So the classification process consists of a number of steps which are described in Part 1A of the ABS Rules for Conditions of Classification. So what are these steps? The first step is the classification process involves the development of rules, guides, and other standards for ships, offshore facilities, and marine vehicles such as submersibles. Then the next step involves design review and surveys to check for compliance with the rules. The next step is classification of ships, offshore facilities, and submersibles once compliance with the rules has been checked. And the next step is issuance of a class certificate that is valid for 5 years and is endorsed annually after conducting post-construction surveys. So how are the class society rules developed? So these rules are developed by class society engineers and surveyors with the assistance of industry experts. Now these rules are then reviewed and approved by committees that include industry experts, representatives of government organizations, shipbuilders, ship owners, operators, etc. So this process ensures that the rules of the class societies are thorough, they are impartial, and they are practical to apply. Next slide. So classification in essence means that the vessels, offshore facilities, and submersibles are in compliance with the applicable rules. So while classification is a process, the owner or the operator also has a responsibility. So what are these responsibilities? They need to operate the submersible within its design or operational limits. Okay, so all submersibles are designed for specific parameters. If you exceed these parameters, then you're likely to have an accident. So it's very important to operate the submersible within its design and operational limits. Then they are responsible for periodically inspecting and maintaining the submersible. Then they are responsible for crewing the submersible with trained and competent personnel. And they're also responsible for following all applicable statutory regulations of the flag or coastal state administration. So all these are responsibilities of the owner and operator. So the rules provide the minimum criteria for classification. However, owners and operators still need to use an independent judgment when they operate the submersible, and safe operation as well as maintenance of the submersible is the sole responsibility of the owner and operator. Next slide. So what is the classification process for submersible? So this involves a number of steps. The first step is rule development. That means we will develop, establish, and maintain recognized technical standards known as the rules. So the rules provide the baseline for classification. Then once the rules are developed, the class society will conduct design review to check that the design of the submersible is in compliance with the rules. Then the class society will conduct material and equipment certification. So this will verify that the submersible meets the rule requirements and all the materials and the equipment is certified and it meets the rule requirements. So next we have new construction survey. So this will check that the submersible is built as per the rules. And then we have surveys after construction. This will check that the submersible is maintained in compliance with the rules throughout its life cycle. So this is done through annual surveys which are conducted at 1-year intervals and special periodical surveys at 3-year intervals. Okay? So this is a little different from surface vessels. Surface vessels have their special periodical surveys at 5-year intervals. So the question comes, why do we have a 3-year interval for underwater vehicles? This is because this comes from the IMO submersible guidelines, which requires dry docking surveys at 36-month intervals. Okay? So this is the basic process for classification of submersibles. So next we come to the ABS experience with underwater units. Next slide. So since the 1960s, ABS has classed around 100 submersibles worldwide. Now these include some of the first commercial submersibles that were developed in the 1960s and 70s, such as the Perry and Pisces submersibles. Now ABS has also classed some of the latest commercial submersible designs that are available in the market, including submersibles built by companies such as Titan Submarines and Seaimagine Hydrospace. Now currently ABS has around 30 submersibles in class. Apart from submersibles, ABS also has 43 diving systems in class. So these include saturation, mixed gas and air diving systems. Then we have one submarine rescue handling system in class for the U.S. Navy. Then we have an undersea habitat in class. So this is the Aquarius habitat, which is located underwater off the Florida Keys. And then we have 3 hyperbaric facilities in class. So these are all underwater units that are currently in class with ABS. Next slide. So when it comes to the OceanGate Titan Submersible, ABS had no involvement with this submersible. No request for class was submitted to ABS, and no design review or surveys were conducted by ABS. Okay. Next slide. So the Coast Guard asked us about the Antipodes submersible. Now this was a submersible that was owned by OceanGate for a period of time, and it was then sold. So this slide gives a brief history of the Antipodes submersible. So this submersible was built by Perry Submarine Builders out of Florida, and then major modifications were conducted by Marlin Submarines. This is a UK-based company. So they conducted major modifications to the submersible. They removed the lockout compartment. And the slide basically gives a brief history of this submersible. Now the important point is this submersible has a traditional steel pressure hull, and it was designed for a depth of 305 meters seawater or 1,000 feet seawater. Now the submersible maintained its classification during the time it was owned by OceanGate, and it is still classed with ABS. So that's a brief summary of the Antipodes submersible. Next slide. So next slide. Yeah, okay. No, previous slide, please. Okay. Now, the modern day submersible industry started in 1948 with the design and development of the Bathyscaphe FNRS-2, which was followed by the development of the Bathyscaphe Trieste. Now, these Bathyscaphes were designed and developed by the Swiss physicist and balloonist Auguste Piccard. Now, subsequently in the 1960s, the submersible industry started taking off as more and more submersibles were designed and manufactured. So these included submersibles for tourism, recreational and scientific research purposes. So at that time, the only available requirements for certification of submersibles were the US Navy requirements, and there were no published industry standards for the certification of commercial submersibles. So ABS was approached by members of the industry as well as the US Navy and Coast Guard to develop requirements for the classification of commercial submersibles. So in response, ABS established a special committee on submersible vehicles that included industry stalwarts such as Jack Piccard, John Pritzlaff, Lieutenant Don Walsh, and ABS developed the 1968 guide for the classification of manned submersibles. Now, this was a pioneering document. It was the first set of requirements for manned submersibles that was published by any class society. Now, following the release of the 1968 guide, this guide was updated and then published as the ABS rules for underwater systems in 1979. It was again updated and published as the ABS rules for building and classing underwater vehicles, systems, and hyperbaric 1990. And this edition of the rules incorporated additional requirements for passenger submersibles. So the latest edition of the rules is the 2024 underwater rules. And these rules are updated every year. And all these rules are posted on the ABS website, www.eagle.org. Next slide, please. So now we come to the materials. So when it comes to submersible design, there are two sets of materials that are very tightly controlled. These are materials for the pressure hull and materials for life support systems. Okay? So the pressure hull is a critical component, and it serves to protect the human occupants for the extremely high hydrostatic pressures that are present at depth. So the pressure hull has absolutely no redundancy or backup. So if the pressure hull fails, you've effectively lost the submersible. Okay? So it is very important that the pressure hull be fabricated from robust materials that have a documented service history for external pressure applications. So the ABS rules require pressure hull materials to be fabricated from approved material specifications, and the rules have a list of approved materials for pressure hulls. So these materials are listed on the screen, and they include steels, aluminum, titanium, and acrylic plastics for the windows. Now, all of these materials have many years of documented service history and are considered to be well-established and robust materials. Now, it's important to note here that carbon fiber composites are not approved materials for the pressure hull of submersibles as per the ABS rules. Next slide. So now we have a couple of questions on carbon fiber pressure hulls. So the first question that arises is, why do we need a carbon fiber composite pressure hull? What are we trying to achieve? Okay. So carbon fiber composites are high-strength, lightweight materials. Okay. Now, a pressure hull fabricated from carbon fiber composites would be much lighter from a hull made from traditional materials such as steel or titanium. Okay. So with a lighter hull, what happens is you can reduce the amount of syntactic foam that needs to be carried on the submersible to maintain buoyancy. Then you don't need a crane or a launch and recovery system for launching and recovering the submersible while you're at sea. And since the hull is lightweight, you can increase the size of the hull and accommodate more passengers. Okay? So typically what we have seen is anytime you go below a depth of 1,000 meters seawater or 3,280 feet seawater, the shape of the pressure hull is spherical. Okay? We have not seen cylindrical pressure hulls being used beyond a depth of 1,000 meters seawater. The reason is a spherical pressure hull is the best shape for resisting external pressure. Okay? The stresses are evenly distributed around the hull. So if you take a spherical pressure hull versus a cylindrical pressure hull of the same thickness, when exposed to the same pressure, you will see that the hoop stress in a spherical pressure hull is half that of a cylindrical pressure hull. Okay? So if you see a cylindrical pressure hull being used beyond 1,000 meters, it is pretty unusual. Okay? So now, what are some of the key concerns with the carbon fiber composite pressure hulls? So the first thing is carbon fiber composite pressure hulls are anisotropic. That is, the mechanical properties vary with direction. Okay? So the mechanical properties are strongest in the direction of the fibers. When the fibers are loaded in tension, that is when the carbon fiber composite is the strongest. But if you go in other directions, the composite is not so strong. So when the composite is exposed to external pressure, the pressure will act perpendicular to the direction of the fibers. And that is not the strongest direction of the carbon fiber composite. Okay? So this is very different from traditional materials such as steel or titanium, which are isotropic. That is, the mechanical properties are same in all directions. Okay? So the next thing is carbon fiber composites are a combination of carbon fiber strands in an epoxy matrix. The carbon fiber is strong in tension, weak in compression. The epoxy, on the other hand, is strong in compression and weak in tension. So the composite is a combination of these two materials. The characteristics of these two materials are combined together to create the composite. Okay. So the next thing is carbon fiber composites do not exhibit plasticity or ductility similar to steels. Okay. So carbon fiber composites, if you look at the stress strain curve of carbon fiber composites, the relationship between stress and strain is nearly linear up to the point of failure. Okay. So this curve does not have a well-established yield point because there is no yielding of the material. So the material goes all the way to its failure point and then it catastrophically fails with little or no warning. So this is very different from traditional materials such as steel or titanium. Because in steel or titanium, once you reach the yield point, the material starts deforming. And then you reach the ultimate tensile strength and it deforms further and then the material fractures. So there is plastic deformation of the material from the yield point till the time it fractures. Okay? And then strain hardening of the material takes place till you reach ultimate tensile strength. And after that, there's something called necking, or the reduction in area of the material. Okay? So this effect is not seen in carbon fiber composites. Okay? So they go directly to the point of failure and then suddenly fail. So then the next thing is prolonged exposure to UV radiation can cause the epoxy to get damaged. Okay? So what happens is the epoxy, in some cases, you add something called a UV stabilizer. It's a chemical that's added in the epoxy, and that protects the epoxy from UV radiation. In some other cases, you can have a gel coat or a top coat which is placed on the epoxy. For example, you can have a polyurethane coating, and that protects the epoxy from the damage caused by UV radiation or the sunlight. Okay? So if you don't have this protection and you expose the carbon fiber composite to sunlight, the UV radiation will degrade the mechanical properties of the composite. Okay? So next thing is under extreme high pressure applications, carbon fiber composites are susceptible to fatigue damage under repeated external pressurization and depressurization. And the accumulated damage may remain hidden and may not show up. Okay? So the important thing here is unless the fatigue failure shows up as cracks or delamination, you really cannot see the damage. It may remain hidden in the carbon fiber strands. Okay? So once you have a crack or a delamination, the extreme high water pressures will accelerate the growth of the crack or the delamination. And the crack will grow very fast. Okay? And then you can have collapse or failure of the pressure hull. So the next thing is carbon fiber composites are notch sensitive. They are sensitive to local damage. So if you have a cut on the surface from a mechanical impact, this can grow to form a crack, which can lead to failure of the pressure hull. Okay, so it's very important to protect carbon fiber composite pressure hulls from impact loads. Okay, and then saltwater ingress in the epoxy matrix under extreme pressures can lead to delamination. Okay, now epoxy resins in general are highly resistant to saltwater damage. However, if you have voids in the epoxy, okay, we have air pockets. Salt water can accumulate in these air pockets, and over time, this can form saltwater crystals. And then over several pressure cycles, this can cause delamination of the pressure hull under extreme pressures. Delamination means separation of the carbon fiber plies. Okay, so that is another damaging effect that is possible in carbon fiber composites. Next slide, please. So one of the processes used for fabricating carbon fiber composite pressure hulls is the filament winding process, in which the pressure hull is created by impregnating or coating the carbon fiber strands with epoxy and then winding them in a precise geometric fashion over a mandrel. So a mandrel is basically a tool in the shape of a cylinder. So on the cylinder, you wind the carbon fibers which are impregnated with epoxy, and then you cure that cylinder in an oven at 1 atmosphere or in an autoclave under pressure. Okay? So in a thick carbon fiber pressure hull, there may be several layers of carbon fiber composites, and these layers cure at different rates. So what you'll have is several layers with different mechanical properties since they were cured at different rates at different times. Okay? So manufacturing a thick section of carbon fiber composites with consistent mechanical properties throughout the thickness is difficult. Okay? So the mechanical properties of the finished product or the finished carbon fiber pressure hull depend on a number of factors. So these include the number of layers and the thickness of the carbon fiber composites. So the more the number of layers and the greater the thickness, the more difficult it is to achieve a pressure hull with consistent mechanical properties throughout the thickness. Another important consideration is the winding orientation. Now, a typical thick shell pressure hull is exposed to hoop stresses, radial stresses, as well as longitudinal stresses. Okay. Now, if your winding is hoop winding, that means if you wind the carbon fiber composites around the cylinder in a hoop fashion, that is only good for withstanding hoop stresses. It cannot withstand radial or longitudinal stresses. So to withstand radial or longitudinal stresses, you typically employ X cross winding. That means you wind it in an X pattern, okay? And that is more effective in handling hoop as well as radial as well as longitudinal stresses. Then the type of epoxy resin that is used for creating the composite has an impact on the strength of the pressure hull. So aerospace grade epoxies may not be suitable for high pressure underwater applications, okay? So then there are other factors such as the epoxy wetting rate. That means how much epoxy can you coat on the carbon fiber strands. Then the epoxy curing rate. If you don't follow the correct curing profile, your mechanical strength may differ. Then humidity is another important consideration. So high humidity during curing of the composite can negatively impact the mechanical properties. This is because moisture absorption in the resin can lead to delamination and reduced interfacial strength between the carbon fiber and resin, thus weakening the composite. Then curing the carbon fiber composite at the proper temperature is very critical. So if you don't follow the exact temperature profile when you cure the carbon fiber composite, then it will affect the mechanical properties. If you don't properly cure it, the mechanical properties can be degraded. So pressure is another important consideration when you cure your carbon fiber composite. So the composite can be cured at 1 atmosphere in a standard oven, or it can be cured under pressure in an autoclave. So autoclave is basically a pressurized oven. So the pressure will basically drive out the air pockets in the carbon fiber composite and will compress the carbon fiber composite. So you get a better product if you cure your carbon fiber composites in an autoclave versus curing it in a 1 atmosphere oven. Okay, so then the other aspect is manufacturing defects such as voids, porosity, blisters, inclusions can have an effect on the strength of the carbon fiber composite. So voids are basically air pockets within the thickness of the carbon fiber composites. Blisters are formed on the surface of carbon fiber composites. Then you can have porosity. Porosity means a large number of voids in a close proximity to each other. So all of these can weaken the carbon fiber composite sections, and under extreme hydrostatic pressure, they can accelerate the collapse of the pressure hull. So the next thing that's challenging is bonding of carbon fiber composites with metallic elements. So typically, if you bond a carbon fiber composite with a metal, what you will do is you'll have projections coming out of the metal. Typically, you will have fins, and these projections go in the carbon fiber composite, and they help in getting better adhesion. So in addition to applying an adhesive, you have to have co-lamination. That ensures you have better adhesion between the carbon fiber composite and the metallic element. Now, galvanic corrosion is an important consideration here because if the metal comes in contact with the carbon fiber strands in the presence of seawater, you can have galvanic corrosion. So this typically occurs in steels and aluminum, and that can cause corrosion of the metallic members. Okay. Next slide, please. So now carbon fiber composites have a low modulus of elasticity, they have low shear strength, and they are brittle materials with low impact strength, okay? So they have very low resistance to impact loads, and the hull is susceptible to deformation under applied external loading. So typically lifting lugs and other attachments are not directly installed on carbon fiber composite pressure hulls because they cannot withstand localized loading, and they tend to deform under localized loading. So then if you install penetrations on the carbon fiber composite pressure hull, that means you have to make openings in the pressure hull. That will weaken the pressure hull because the main load-bearing member in a composite are the carbon fiber strands. So if you cut the strands to make an opening, you're going to weaken the pressure hull. So reinforcement of the openings is very critical. And if you don't reinforce it, you can have stress razors in the vicinity of the opening, and that can lead to cracks and failure of the pressure hull, okay? So then when you design your carbon fiber pressure hull, you also need to consider various failure modes, including delamination, debonding, fiber breakage, and matrix cracking, okay? So delamination basically means separation of the carbon fiber plies. The plies start separating. Then debonding basically means when the carbon fiber strands start coming out from the epoxy matrix, okay? So debonding is caused by failure of adhesion between the strands and the epoxy matrix, okay? And then matrix cracking is basically characterized by cracks in the epoxy matrix, and this occurs due to fatigue of the material. Fiber breakage occurs when the carbon fiber strands will snap or break, okay? So this can be caused by high stresses, they can be caused by impact loads, or due to manufacturing defects in the carbon fiber. Now, since the carbon fiber strands are the main load-bearing member in the composite, if you have strands that break off, then the strength of the hull will deteriorate and you can have premature collapse of the pressure hull, okay? So then when it comes to metallic pressure hulls, there are well-established failure modes and factors of safety that have been proven over many years of service experience, okay? So the figures on the screen show some of the typical failure modes for metallic pressure hulls. The first figure shows local yielding. So local yielding occurs when the section of the pressure hull between two adjacent stiffeners fails. Okay, you have yielding between two stiffeners, and then the hull will take the shape of an accordion pleat. So that is called local yielding, and the factor of safety for local yielding in the ABS underwater rules is 1.5. Then you can have local buckling. Local buckling occurs when the section of the pressure hull between two stiffeners buckles. Okay, so you'll have dimples formed in the pressure hull, and that is known as local buckling or low bar buckling. And the factor of safety for this buckling in the ABS underwater rules is 1.25. And the third failure mode, which is the figure on the far right, is general instability or overall collapse of the shell and stiffener section, okay? And the factor of safety in the underwater rules for this failure mode is 2.0. So all of these failure modes are well established, they have many years of service experience, and the factors of safety are well proven through service experience on many different submersibles. Now, additionally, the rules also have a well-established acceptance criteria for hull out of roundness and local departure from design geometry. So when you have a pressure hull which is exposed to external pressure, it is very important to maintain out of roundness of the hull, okay? So if the out of roundness of the hull goes beyond specifications, it can cause premature collapse of the hull. So out of roundness is absolutely critical when you have a pressure hull which is exposed to external pressure. Next slide, please. Okay, so currently there are no recognized national or international standards for carbon fiber pressure hulls for human occupancy, okay? So we have the ASME Boil and Pressure Vessel Code has section 10, which addresses fiber reinforced plastic pressure vessels. But if you look at the scope of section 10, it states that pressure vessels of human occupancy are not covered under this code. And then we had a look through this code. It addresses pressure vessels that are used for surface applications. It really does not address pressure vessels that are used for deep sea diving applications. We had a look at the testing requirements. So many of the testing requirements are geared towards internally pressurized pressure vessels. We didn't see any specific testing requirements for externally pressurized pressure vessels. Okay, so these are some of the shortcomings of section 10. And this section is not applicable to manned pressure hulls, okay? Nevertheless, it has a lot of useful information. It has acceptance criteria for voids, delamination, cracking, etc. The important thing is this code states that for a new construction pressure hull, no delamination and no cracking in the matrix is permissible, okay? So if you have a new hull with delamination or cracks, it is not acceptable as per this code. Okay, so when it comes to carbon fiber composite pressure hulls, you know, the different failure modes, the factors of safety, as well as the other acceptance criteria is not really defined in international standards, as well as class society rules, okay? So one of the very important failure modes for thick shell carbon fiber composite sections under external pressure is snap-through buckling, okay? Now, snap-through buckling is an effect that has been observed in subsea pipelines made of glass fiber reinforced plastics, okay? Now, this buckling causes sudden and catastrophic failure of the pressure hull, okay? And it is thought to be triggered by shape imperfections. For example, if there is out of roundness, that can trigger this buckling. Okay. Now, snap-through buckling is different from traditional buckling, which is caused by progressive overpressurization of the pressure hull beyond its design depth. So when snap-through buckling occurs, it causes instantaneous delamination of the pressure hull and instantaneous collapse of the pressure hull, which can occur in less than a millisecond. Okay. So if you have sensors for real-time monitoring, it will not pick up any signs of this failure before it occurs. Okay. Now, snap-through buckling is a phenomenon that is not yet well understood. Okay. So additional theoretical and experimental research is needed to determine what are the factors that cause this failure mode, what factors of safety are needed to avoid this failure mode, and what do we need to do to guard against this failure mode. So this is something that is not addressed in international standards. It is not well understood. Nevertheless, this effect has been observed, and we need to have further research and testing in this area. Okay, so the other thing is when you do your design calculations for carbon fiber composites, these materials are anisotropic. That means the mechanical properties vary with direction. The mechanical properties through the thickness may vary. Okay. And they're also dependent on the manufacturing process. So all of these can vary the mechanical properties of the finished product. So when you do your design calculation, it's very important that you test coupons from the as-built product. So how this is done is you will typically extend the length of the cylinder. Okay, this is called prolongations. And from there you will cut coupons. Coupons are basically sample of materials that you then send to a lab for testing. So after it's sent to the lab for testing, you will evaluate various mechanical properties. These include the tensile properties, what's the ultimate tensile strength, what's the tensile modulus, the compressive strength, the flexural strength, the shear strength. All of these properties are evaluated, and then you'll get the test results. And those test results are what is used for your design analysis. Okay. So if you don't use those test results, what you design may not match what you have produced. Okay. This is a little different from traditional, pressure hull materials, because when we do the design review of traditional pressure hull materials, the material allowables and the mechanical properties come from the material specifications. Okay, you typically do not use the as-tested mechanical properties because they may exceed the material allowables. If they don't exceed, the material is rejected. Okay, but the as-tested properties are typically not used when you design pressure hulls made of steel or titanium, because the properties you use there come from the material specification. Those define the minimum acceptable properties. Okay, next slide, please. So next we come to non-destructive inspection of thick carbon fiber sections. So if you have a very thick carbon fiber section, for example, a 5-inch thick section, ultrasonic examination may not be suitable because of lack of penetration of the ultrasonic waves and lack of reflection. Okay, so using UT, you may not be able to evaluate a thick carbon fiber composite section. So for thick carbon fiber composite sections, you will use non-destructive techniques such as X-ray computed tomography, or you can use active thermography. Okay, so X-ray computed tomography, basically you have an X-ray machine that goes around the circumference of the pressure hull, and you have various slices. You have images in slices. All these images are combined together using software, and you get a 3D image of the hull. Okay, then you have an in-depth look what is going on inside the hull. So this inspection basically requires you to strip down the pressure hull. So if you have a pressure hull that is in service, and now you need to do a non-destructive examination, you need to remove all the equipment, or all the outfittings on the pressure hull. Okay, now if you do not have this equipment at the facility where you're maintaining the submersible, then you need to ship the submersible hull to another facility where they have this specialized equipment. Now, after doing the ND, if repairs are required, you may need to repair the pressure hull, okay, and then ship it back. So all this is an expensive and a long process, and it may not work practically for a submersible that is in operation, because you need to take it out of operation for many months at a time. Okay, so these are some of the challenges that you will face if you use a carbon fiber composite pressure hull. Okay, next slide, please. So for carbon fiber composite pressure hulls, it is very important to verify that no deformation is taking place, no degradation is taking place, or no flaw development is taking place that may weaken the pressure hull. So these needs to be done periodically over the service life of the pressure hull. Now, the post-construction inspection and testing criteria for carbon fiber pressure hulls are currently not addressed in recognized international or national standards. As a minimum, they should address non-destructive examination criteria, okay? So what kind of non-destructive examination is required? What is the periodicity, and what is the acceptance and rejection criteria for this examination? Then what are the dimensional measurement criteria for out of roundness and local departure from design geometry, okay? So how much out of roundness is permissible? This is currently for a carbon fiber composite pressure hull. This is currently not addressed in international standards. And then what are the test dive requirements periodically for carbon fiber pressure hulls? Okay, so all of these are not addressed currently and they need to be addressed. Next slide, please. So then the question comes up, do existing class society rules, statutory regulations, or industry standards address carbon fiber pressure hulls for submersibles? So under the ABS underwater rules, carbon fiber pressure hulls are not acceptable materials for submersibles. Now, to the best of our knowledge, the requirements of other IX member class societies, as well as existing industry standards or statutory regulations, do not have specific requirements for carbon fiber composite pressure hulls. Okay. Now, we are aware that a number of ASME PVHO cases have been developed for the use of non-metallic materials for pressure vessels or human occupancy. Okay. So what is an ASME PVHO case? Now, if a designer or builder wants to deviate from the published requirements of the ASME safety standard, then they develop something known as an ASME case. Okay. So this ASME case is then submitted to the ASME PVHO Standards Committee, and the Standards Committee will review the case and then they will approve it. Okay. Once the case is approved, it is they place it on the ASME website. Okay. So all the published cases are put up on the ASME website, and anyone can use a published case. So ASME has a mechanism by which, if you want to deviate from the published requirements, you develop a case, and that is published, and it is put on their website. So this is similar to the code cases that are developed for the ASME boil and pressure vessel code. Okay, so a lot of code cases have been developed. Now, some of the ASME PVHO cases that have been developed are for surface-based internal pressure applications. For example, medical hyperbaric chamber, transfer trunks for diving, etc. All of these operate at relatively mild pressures. So these operate in the range of 4 to 80 psig. Okay. So in comparison, if you go down to a depth of 4,000 meters seawater, the pressure there is 5,800 psi. Okay. So there's a huge difference between the pressures for these ASME PVHO cases versus the external pressure at a depth of 4,000 meters seawater. Now, case number 11 addresses a non-metallic expansion joint that was used as a transfer trunk or tunnel between two pressure vessels of human occupancy. This was designed for the Navy submarine rescue system. Okay, this is basically an expansion joint that connects two PVHOs. And the materials used were neoprene, polyester, and a fluoroelastomeric compound. Then case number 12 was a non-metallic portable hyperbaric stretcher, and the material used was a liquid crystal polymer tube which was enclosed in polyurethane and which was then coated with nylon. And the maximum pressure for this application was in the range of 33 to 75 psig. So all of these are for internal pressure applications, and they are for very mild pressures as compared to the pressure at a depth of 4,000 meters seawater. Okay, next. So then the question comes up, do class society rules allow you to use alternative requirements or equivalent standards for carbon fiber PVHOs? So while the ABS rules do have provisions for alternative arrangements and novel concepts, in the many decades that we have been classing submersibles, these alternatives have not been used for carbon fiber pressure hulls. Now, if you have non-standard designs, materials, there is a mechanism in the ASME PVHO standard by which you can get approval. Okay. So if you look at the ASME PVHO standard, non-mandatory Appendix D has guidelines for developing a PVHO case for the use of non-standard materials or non-standard designs. Next slide. So this slide basically gives a brief overview of non-mandatory Appendix D in the ASME PVHO 1 standard. And these are basically guidelines for qualifying non-standard designs and non-standard materials. So as the first step, detailed design information on the proposed materials along with the detailed design analysis, which consider all applicable loads and environmental conditions need to be developed. Thereafter, you have to conduct prototype testing. So this testing involves, there is proof pressure testing. So for this proof pressure testing, 3 full-scale pressure hulls are tested to 6 times maximum allowable working pressure or MAWP without failure. So this is basically a factor of safety tests, okay? So you will test the hull to 6 times its design pressure, and if it does not fail, that qualifies the design. The next testing is creep testing. So under creep testing, so what is creep? Creep basically means under sustained hydrostatic loading, does the pressure hull deform? Okay, that is creep. So for creep testing, you will use model or full-scale pressure hulls, and they are subject to 10,000 hours of sustained pressurization without failure. So 10,000 hours basically means 1 year and 1.5 months. So you will pressurize the hull and maintain the pressure for 1 year and 1.5 months, and then you check if the hull has deformed or it has failed by creep. Okay. So the options available include you test 1 pressure hull to 3 times MAWP, or you test 5 pressure hulls to 2 times MAWP. So after the creep testing, the next thing is a cyclical pressure testing. This is basically a fatigue test. So then you take a full-scale pressure hull, and then you will cyclically pressure test the hull for a number of pressure cycles. So the approved operational pressure cycles will basically be half the number of cycles you tested minus 1,000 cycles. Okay, so that is how you get the fatigue life of the hull. So once you conduct the prototype testing, you have qualified the prototype. So the next thing is you build the production unit, and thereafter you'll do a hydrostatic pressure test to 1.5 the design pressure, and then you'll maintain the pressure for 1 hour. Now for this case, all the testing needs to be witnessed and signed off by a third-party independent agency such as a class society. Okay, so these guidelines provide very, very clear requirements for non-standard designs and materials. You can follow these guidelines anytime you have non-standard designs or materials. So there is a mechanism in the industry for qualifying non-standard designs and materials. Next slide, please. So then when it comes to hydrostatic pressure testing requirements for pressure hulls, what are the ABS rule requirements? Now these rule requirements are for metallic pressure hulls, okay? So the ABS rules require your pressure hull to be hydrostatically pressure tested to 1.25 times the design depth for 2 cycles, okay? And when you do this pressure testing, you have to strain gauge the pressure hull. Strain gauges are to be fitted in way of hard spots and discontinuities. Hard spots is a spot where the hardness is slightly different from the other sections of the hull. Discontinuity could be a sudden change in the geometry or the loading or the material of the hull, okay? So all of these spots would be strain gauged. And then the strain gauge measurements are recorded after shakedown effects have ceased, okay? So the question comes, what is shakedown, okay? So in a new construction pressure hulls, you will notice their localized area of high stresses on the hull. So when you pressure cycle the hull above its design pressure, what happens is these localized area of high stresses start deforming, okay? So you'll have localized deformation and then strain hardening occurs. Once the strain hardening occurs, no further deformation of the hull occurs plastically. All the deformation is in the elastic region, okay? So that is when the shakedown effects cease. So what happens if you pressure test the hull and start recording the strain gauge measurements before shakedown has ceased? You will note that the strain gauge measurements on the first and second cycles do not match. That is because shakedown is still taking place. So after shakedown has ceased, you will see the pressure, the readings on the strain gauge on the first and second cycle, they will match, okay? So typically to verify that shakedown has ceased, you will pressure cycle the hull for a number of cycles, and then you will check the strain gauge readings. Once you confirm that the readings match, that is the point when shakedown has ceased, okay? And those are the readings you actually use for your hydrostatic pressure testing. So then once the hydrostatic pressure testing is completed, the designer will submit a report comparing the calculated stresses versus the measured stresses. There should be a good correlation. If there's not a good correlation, we'll ask the designer to justify what's happening. Why is the calculated versus the measured stresses varying, okay? And then once the hydrostatic pressure test is completed, you'll have non-destructive examination of the hull. So this is done by surface ND techniques such as magnetic particle testing, dye penetrant testing, or eddy current testing, okay? And then out of roundness measurements are taken, and then we verify compliance with the acceptance criteria in the ABS underwater rules, okay? Now these out of roundness measurements after hydrostatic pressure testing are used as reference measurements throughout the life of the submersible, okay? So 5 years down the road, if you want to check what were my original readings, what my readings now, these are the reference readings that you will use throughout the life of the submersible. So it is very important to have a reference set of readings which you will use for the life of the submersible. Next slide, please. So then we come to the ABS rule requirements for test dive of new construction submersibles. So after the pressure hull is built and it is fully outfitted, we conduct a test dive. Okay, so before passengers get on the submersible, you have to do a test dive in the presence of the ABS surveyor. So how do you do this test dive? Okay, you start diving and you increase your depth at 20% increments. So you first dive to 20% of your design depth, you stop, and then you will start internally inspecting all your wells, all your hatches, you will inspect your windows, and you will check your pressure boundary valves, make sure there are no leakages, okay? If everything is good, then you continue test dive for another 20%, okay? In this manner, you keep going down till you reach your test depth, okay? And once you reach your test depth, you functionally test all your systems, your life support systems, your electrical systems, and other essential systems, okay? So this is a test dive. This qualifies the submersible for diving at that particular depth. Sometimes what happens is when you go for doing a test dive, the depth of the water may not be equal to your design depth. Your design depth may be deeper than the dive at which you tested the submersible, okay? So the depth at which you tested the submersible is known as a rated depth, okay? So when we class a submersible, we will class it for the rated depth, okay? And later on, if you want to increase the rated depth, you can do another test dive, okay, beyond the rated depth, but not exceeding your design depth, okay? So there are two depths that are very important, design depth and rated depth, okay? Next slide, please. So then we come to post-construction surveys. So during the annual surveys, this is basically a visual examination of the pressure hull. So the surveyor will go and inspect the pressure hull. They will inspect the hatches, the ceiling surfaces, penetrations, the welded joints, viewports, foundations, and the shut-off valves on the pressure hull. So this is a visual examination to make sure that there is no degradation, there's no leakage, etc. And this is done every 1 year. Then the special periodical surveys are conducted at 3-year intervals. Now, during this survey, we have enhanced examination of the pressure hull. So this requires removal of your protective coatings as well as thermal insulation in selected locations. And then if you have highly stressed parts such as the lifting lug wells, they are non-destructively examined using surface ND techniques such as dye penetrant testing, eddy current testing, etc. And then if the surveyor suspects that there is deformation of the hull or there is damage to the hull, then the surveyor may require out of roundness measurements to be taken for the hull. And these would be compared with the reference measurements as well as the acceptance criteria specified in the rules. So if you exceed the acceptance criteria in the rules, then the pressure hull is rejected. Okay, you have to repair the pressure hull, bring it back in spec. Otherwise, you cannot dive. So then we also require a test or operational dive. So during the annual surveys, we require an operational dive to be conducted every year. And during our special periodic surveys, we require a full depth test dive to be conducted in the presence of the surveyor. And this dive is to demonstrate proper functioning of the systems and equipment at the full depth. Okay, next slide. So then we come to the IMO submersible guidelines. So these guidelines were developed by the International Maritime Organization, or IMO, back in 2001, okay? So the intent of these guidelines was to provide an international standard that could be used by flag administrations around the world, okay? Now, compliance with these guidelines is voluntary since the IMO Solus Convention does not mandate that you have to comply with these guidelines. So compliance is voluntary. Unless the flag administrations require to comply with these guidelines, designers or operators may not comply with these guidelines, okay? And then these guidelines require the pressure hull, materials, fabrication and testing to comply with the requirements of a recognized organization to the satisfaction of the administration, okay? So a recognized organization is typically a class society, okay? So if you want to comply with the IMO submersible guidelines, it means that your pressure hull needs to meet the requirements of a class society. So then it also requires the issuance of a design and construction document by the administration. So this document will list the standards, the design and construction standards for the submersible. And then it also requires the administration to issue a safety compliance certificate after the initial surveys of the submersible are conducted. So typically the design review and surveys would be conducted by a recognized organization, such as a class society, on behalf of the flag administration. And then this submersible guidelines also require the management of the passenger submersible operations to comply with the International Safety Management Code, or ISM code. Okay, so that's a brief overview of the IMO submersible guidelines. Next slide, please. So then we come to the U.S. Coast Guard Navigation and Inspection NVIC Navigation and Vehicle Inspection Circular 593. This provides guidance for the certification of passenger submersibles. So these guidelines were developed back in 1987 when the Atlantis passenger submersibles were being classed. The Coast Guard worked closely with Atlantis, and these guidelines were developed. They were tailored to the Atlantis submersibles. Okay, so currently, if you're under 100 gross tons, okay, subchapter T of 46 CFR has requirements for passenger vessels under 100 gross tons, but these apply to surface vessels. Okay, these typically do not apply to submersibles. So to develop equivalency to these requirements, this NAVIC was developed, and this was published back in 1993. So now this NAVIC applies to submersibles carrying one or more passengers for hire. This is as per the 1993 Passenger Vessel Safety Act. Okay, and this requires the pressure hull to meet the ASME PVHO standard or the ABS underwater rules. Now this NAVIC applies to US flag submersibles or submersibles operating in the US jurisdiction. So it does not apply to non-US flag submersibles or submersibles operating in international waters. Okay, so that's a brief overview of this NAVIC, and that's all I have in the slides.
Thank you, sir. Appreciate your willingness to answer some questions from the Marine Board in that presentation.
Absolutely.
We'd like to take a short recess to formulate some questions, follow-up for you, sir. So at this time, the hearing will recess and reconvene at 12:10. This hearing is now back in session. Sir, Commander Whalen has some questions at this time.
Again, thank you, sir. Does ABS define passenger?
Yes.
And where is that defined at?
So we have a section in our rules which addresses definition section 2. So that's where it addresses passenger. I can just read out the definition for you. So passenger is every person other than the pilot and members of the crew or other persons employed or engaged in any capacity on board the submersible on the business of that craft. So this definition is also present in the IMO submersible guidelines, the same definition.
Regarding the IMO submersible guidelines, are you aware of any nations or flag states or administrations that require, as stated, for the applicability, that require them to conform to those standards?
I'm not aware because we have Bahamas, which has their own regulations. Cayman Islands has their own submersible regulations. The UK has their own regulations. And I don't believe the US Coast Guard accepts the guidelines. Yeah? So you have your own NAVIC 593. I'm not aware of any countries that are using these guidelines. Yeah?
Thank you.
And that's perhaps because it's not mandatory under SOLAS. Yeah?
Under SOLAS, are there any requirements regarding submersibles?
There are no requirements, specific requirements for submersibles in SOLAS. Yeah?
You had mentioned the 2023 diving code. What is the applicability of the 2023 diving code? Do you know offhand? Or?
So yeah, this applies to diving systems that are operated off ships or offshore facilities around the world. It's an optional code, it's not mandatory. So if the flag administration wants you to comply, then you comply with it. But other than that, it's an optional code.
Does this extend to submersibles or submarines operating in support of scientific research?
No. So it strictly addresses diving systems.
Would a submersible be considered a diving system?
No.
Are ABS surveyors permitted to go aboard a submersible for testing dives in performance of their duties?
Yes.
Thank you, Mr. Thomas. That's all the questions I have, sir.
Sir, Commander Williams now has questions for you.
Absolutely.
Thank you, sir. Mr. Thomas, are you familiar with the use of acoustic emission sensors and strain gauges on carbon fiber?
So this is not commonly used in submersibles, but I'm aware that, yeah, they're used occasionally, yes.
Do you have experience with that type of monitoring system?
No.
Earlier, you mentioned conducting mechanical property tests on carbon fiber. When you conduct mechanical property tests of a material, if your mechanical properties are not consistent, what value would you use? Specifically, would you use the most conservative value, or is there criteria where you may just reject the testing itself or the material itself?
Yeah, so first of all, you have to see what is the specification for the material, what are the minimums in the specification. So if you go below the minimums, you will reject the material, okay? So that is the first thing. And then if your mechanical properties are not consistent, if you see a large variation, then we'll have questions, how are you going to assess it during, your design calculations, because there's such a large variation. So when we use pressure hull materials, we prefer materials which have consistent mechanical properties. It's just steels or titanium. The mechanical properties are consistent. You either meet the spec or you don't meet the spec. So most of the submersibles that we have accepted, the mechanical properties exceed the spec.
You mentioned the testing for non-standard designs and materials contained in the non-mandatory Appendix D of ASME PVH-01. Are you aware if ABS has been involved in any non-standard design qualification?
So we have not used that appendix for any non-standard designs as far as ABS is concerned.
We heard testimony last week about two separate incidents that occurred on the Titan Submersible. The first incident involved the forward dome falling off and hitting the deck below. In a situation like this, had the submersible been classed by ABS, would an ABS surveyor have been required to ensure the submersible was safe prior to conducting additional dives?
So yeah, typically in these situations, the surveyor goes and does a damage assessment survey. So we look at the window, we see what kind of damage is there. ASME PVHO standard has criteria for damage, assessing the damage, So what kind of damage is acceptable? So there's a go, no-go criteria in the standard. Assess the window to that criteria, okay? If required, repair the window, then you'll hydrostatically pressure test the window, install it back, do a leak test, do a test dive, show us that everything is okay, and then you can dive, yeah?
The second incident was related to a loud bang that was heard upon resurfacing. In a situation like this, had the submersible been classed by ABS, would an ABS surveyor have been required to conduct an investigation to make a determination for the cause prior to the company conducting additional dives?
Absolutely. So the onus is on the owner or operator. So they need to inform ABS because our surveyors are not present 24/7 on the submersible. If the owner or the operator hears a loud bang or sees any other problem, they need to inform ABS. Then our surveyor will come and do a survey. They will reach back to the technical office to get additional, expert opinion, and then we'll go from there. But if you see a problem on a submersible, stop, ask for outside opinion because this is a dangerous business, yeah? You dive under the water, there is extreme external pressure. So you should not be taking any risks. Contact ABS immediately and then we can look into the issue further.
Since you began working with submersibles with ABS, has there been any catastrophic loss of any classed submersible?
No, none that I'm aware of.
Thank you. That concludes my questions.
Sir, just a couple follow-up questions. You mentioned out of roundness was a primary criteria you monitor.
Yes.
Is that to check for metallic deformation primarily?
Yeah, in the fabrication procedures, when you fabricate your heads or your cylinders, have you fabricated it properly or is it, out of spec?
If a carbon fiber hull was designed to be 5 inches and was out of roundness in the beginning by a certain amount. Would that be problematic?
It would, if it exceeds the specs or the allowables and the rules, that is a problem, because if you exceed your out of roundness limits, it can cause premature buckling failure of the hull. So they have done a lot of, the Navy did a lot of testing on, hulls. They introduced out of roundness on metallic hulls, and then they tested these hulls to failure. And what they noticed is, as you exceed your out of roundness limits, the pressure at which the hull collapses is much less than the design pressure.
And sir, was that just primarily for metallic hulls?
Metallics, yeah.
Do you think the same principle would apply for a carbon fiber hull?
Absolutely, yes.
Sir, I believe you mentioned that you survey critical systems on submersibles.
So I'm a design review engineer, so I'm at the design office, yeah, so I'm not a surveyor.
Oh, I'm sorry, or ABS
Yes.
checks for that,
Yes.
sir. Did you say that life support systems on submersibles was something that ABS would
Absolutely.
survey?
Yes, it's a critical item because, that provides the breathing gases for breathing. It scrubs the carbon dioxide that's produced by human beings. And so it provides the conditions to sustain human life. And it is absolutely critical on a submersible. So we do the design review. We check the materials very carefully because you don't want to introduce contaminants. Some of the items, you can have oxygen system fires. So we look for the materials in oxygen systems very critically, okay? What materials are you using? Are they compatible with oxygen? Can they lead to oxygen fires? So life support systems is absolutely critical, and we also have qualification tests for life support systems, okay? So you'll do, before you even do a test dive, when you're on the surface, you will do a manned life support system test. That means people get inside the submersible, you close the hatches, you run your life support system, and then you monitor all the parameters. So we have extensive requirements for life support testing. And then we also have requirements for off-gas testing. That means if you put non-metallic materials in the pressure hull, they will off-gas volatile compounds. Some of them can be toxic if they accumulate for long periods of time. So we have off-gas testing requirements for the pressure hull as well. So life support systems is absolutely critical.
Are there any other critical systems that you check for a submersible?
Yes, so the other critical system is the ballast and emergency surfacing system. So once you go down, you need to come up, yeah? So if there's an emergency, how do you come up? So they had an accident many years back called Pisces 3 submersible accident. So the Pisces 3, the aft compartment had a hatch that was open, okay, while it was on the surface, and water got in the hatch, it got flooded, and the submersible started descending, okay? And then they dropped the drop weights, the emergency, the ballast weights. The submersible still did not surface. It kept going down. So now we have a requirement in the rules. If your largest single floodable volume, other than the pressure hull, is flooded, and you release your drop weights, you should still be able to surface. So ballast systems is another critical item that we look at.
Thank you, sir. I'd like to pass the questioning to the NTSB at this time.
Yes.
Hey, good morning, Mr. Thomas, and thank you for the detailed presentation. It actually answered most of my questions, but I do have a few follow-ups.
Yes.
Does ABS do statutory inspections as an RO on behalf of any flag states on manned submersibles?
Yes, where we are authorized by the flag administration, we do conduct statutory inspections, yes.
Which flag states might that be?
I think we did some for Cayman Islands, if I recall, or Bahamas. I'm not sure, I'll have to check, but
Okay.
I believe we have done some for some of these flag administrations.
Do the class rules discuss requirements for surface tenders of manned submersibles anywhere?
So the underwater rules basically address the submersible aspects. The surface aspects are addressed in the requirements for surface vessels, yeah? But I'll tell you, like when it comes to integration, for example, if you have a dive system is integrated with the vessel. So you have a launch and recovery system that's on the vessel, surface chambers on the vessel. So we have integration requirements for dive systems that are installed on vessels. But when it comes to submersibles, they are operated independently of the vessels, unless it's a tethered submersible. If it's an untethered submersible, once it's launched, it doesn't need anything from the surface support vessel except they will track the submersible. But the submersible operates independently, okay? And in some cases, the submersible need not be recovered on the vessel. It could be towed behind the vessel, okay? So if it is recovered using a launch and recovery system, we have requirements for launch and recovery system. But those requirements are optional. So if the owner or operator wants to certify the handling system, then they can come to us, we can certify it. But for a class submersible, handling system certification is not mandatory. So that is something that the owner or operator, the onus is on them. If you want your handling system to be certified, then you will ask for certification. Other than that, handling systems and other cargo gear, the certification is optional.
Are those requirements in the rules for cargo gear, or are they in the man-submersible rules?
Man-submersible rules has section 20, which addresses handling systems for man-submersibles, diving bells, etc.
I saw in the rules where it talks about communication, navigation, lighting. Is there other operational issues covered, like training, emergency response, safety management? Are there any of those requirements?
So those are covered under jurisdictional authority. Yeah? So training, competence of the crew is not addressed by class requirements. So the onus for that will fall on the flag administration.
And this is where I'm going to jump around a little bit. Your 2-day ABS Academy class, what incidents do you talk about?
So we talked about the Pisces submersible accident, Johnson sealing accident. Then we had a lithium battery fire in a Russian submersible called Losharik, so we addressed that. Then we looked at some of the submarine accidents, the Thresher. Then we looked at the Greyback accident. And there are a lot of other accidents that we look at, yeah? So we looked at a couple of diving accidents. Then the Sea Lab was undersea habitat, so they had an accident there, we looked at that. So each module covers different accidents, yeah, apart from the rule requirements.
You mentioned experts group on lifting gear and another one on diving systems.
Yes.
What subcommittees do they report to?
MSC.
Directly to MSC, not
Yeah, they report to MSC and
not SSC or SDC or.
I think it may be SSC and then SSC reports to MSC, yeah. Maybe wrong.
Sorry, Mr. Chair, I don't know what those acronyms stand for.
But
SSC is ships design or ships equipment, safety equipment,
yeah, I think it's ship structures and equipment, and MSC is Maritime Safety Committee, yeah.
and SDC is design and construction.
SDC is design construction, yes.
When you talk about the best shape for would be a sphere, and that's below 1,000 meters. Is that a requirement anywhere, either by class or by PVHO?
It's not a requirement, but it's a concept that is well understood by designers, yeah. So if you are an experienced designer on submersibles, there's something that you know. So it's discussed in textbooks, but it's not a class requirement.
What would be the best coating to put on the outside of my carbon fiber submersible that would still allow for NDT and visual inspection and protect from UV and erosion and impact loads?
So I won't know the answer for that. So that's still under discussion, because once you put a coating, how do you examine the hull? How do you see what's happening below the coating? Yeah,
Right.
It's challenging. So I don't know the answer. That needs to be examined further by the industry. Yeah?
Do the rules or the guidelines require an FMEA or an FMECA at all?
Yeah. So if you have a novel concept or if you have an alternative requirement for the rules, then our rules require that you conduct a risk assessment. Okay. And if it's a novel concept, the risk assessment is done in 2 phases. So during the conceptual design phase, approval and principle phase, we'll use a qualitative risk assessment methodology such as FMEA, HAZOP, HAZARD, etc. And then when it comes to the detailed design review phase, we expect you to use quantitative risk assessment techniques such as quantitative risk assessments, emergency systems, survivability assessments, etc. Because at that point, you have a little more data on the design of the submersible. So it's done in 2 phases, and we do require that. Then for certain technologies, we require risk assessment. For example, lithium batteries. If lithium batteries are installed on submersibles, due to the additional hazards posed by lithium batteries, we require risk assessment. Then for passenger submersibles, we require a dive site hazard assessment to be conducted, because you have to go and assess the site before you put passengers, and then you go and dive on that site. Okay. And then when it comes to the operations manuals for submersibles, we require that you have specific operating procedures for emergency scenarios, including fires, contaminated breathing environments, entanglement, etc. So all of these are requirements in the ABS underwater rules.
That requirement to have an operations manual with all those items, that's in the class rules?
Yes, it's in the class rules under part 1 of the rules.
Can you touch a little bit on exotherming and how you can control for that in thick hulls?
Which one?
Exotherming, it's when, I guess, as you cure the hull, it cures at a different rate from inside to outside.
Oh, yeah. So I'm not familiar with the exact. What happens is when you cure the hull, they will have a curing profile. Okay, so the curing profile needs to be defined, and then you need to follow that curing profile when you actually cure the composite pressure hull. So that will be specified by the designer or the builder. They need to look up a code and see, what is the curing profile, and then you have to follow that. So if you don't follow that profile, you can have a product that has mechanical strength well below what you're looking for.
Lastly, I know you said there are no classed carbon fiber submersibles that you're aware of. Have there been any attempts to class a carbon fiber submersible?
So back in the 70s, they had a company called Vickers Oceanographic, okay? And then they built a couple of carbon fiber, I think it was glass fiber reinforced submersibles back in the 70s. So they included, they had the Perry 15 series of submersibles. They removed, I think, the metallic pressure hull, and then they put a glass fiber reinforced pressure hull. And then they built a couple of other submersibles. I think it was L1, L2, L3, and L5. And then they built the LR5. So LR5 was used by the British Navy for their submarine rescue. It was a British Navy rescue submersible, and it had a glass fiber GRP command compartment in the front. Okay, so that was done back in the 70s, and then recently, back in I think 2008 to 2015, they had the Deep Flight Super Falcon and the other submersibles that were built. I believe they were classed with Lloyd's. Lloyd's rules doesn't have any specific requirements, so I don't know what happened there, but I believe those submersibles were classed with Lloyd's. Yeah,
And thank you for your time today, Mr. Thomas.
absolutely.
Mr. Thomas, I think you mentioned FMEA, the acronym during that. Can you define that, sir?
It's a failure modes and effects analysis.
Thank you. At this time, I'd like to go to Ocean Gate Council for any questions.
No questions, thank you.
Does the board have any questions? Mr. Fawcett.
Good morning, sir.
Good morning.
For critical components such as ballast systems and life support systems in a class submersible, can off-the-shelf components be purchased without certification and testing under class rules for the ABS?
So we require a surveyor to be present for the fabrication of critical components. It has to be built under ABS survey. The design has to be reviewed. So typically, if there is a requirement in the rules, then ABS survey will witness the fabrication, and then we will do the design review. Off-the-shelf components typically include lights, cameras, thrusters below 25 kilowatts. Those are some of the typical off-the-shelf components that we accept. They still have to be performance tested during your sea trials. But any critical system that has rule requirements, we require a design review, and we require surveyors to be present for the surveys.
Thank you, sir.
Mr. Thomas, I'm curious if you feel comfortable answering questions about the maintenance of a carbon fiber hull.
So I don't have experience with the maintenance, but I can answer any general questions you may have.
We're aware that the Titan was stored outdoors in the elements over the course of a winter cycle of thawing and freezing temperatures. Would that give you any concern, sir?
So if you have a carbon fiber composite pressure hull, part 2 of our rules has requirements for storage, storage of the raw materials as well as storage of the finished product. And what part 2 of our rules says is you have to store it in a controlled environment. It has to be well ventilated, away from the sunlight. The temperature has to be controlled between 60 and 90 degrees Fahrenheit. Humidity has to be controlled. You should not exceed 80% relative humidity. So the storage of the finished product should be in a controlled environment. You expose it to the elements, it can possibly cause degradation of the material, okay, which is, because this is a composite, it's little different from steels and titanium, which are a little more robust materials, and they can take a little more wear and tear. So, from our side, looking at our rule requirements, we recommend that carbon fiber composite hulls be stored under controlled conditions.
Thank you, sir. Are there any further questions from the board at this time? Mr. Thomas, is there anything that we haven't asked you that you think would be valuable to this investigation?
Well, going forward, so what can we do from here? So I would recommend, that at least the IMO SOLAS convention look into whether they want to mandate, compliance with the IMO submersible guidelines. Because what happens in international waters beyond the territorial waters of different countries, yeah? You take a submersible operated in international waters, what regulations are going to cover it, okay? So the US regulations only apply in US waters, yeah? What happens in international waters? What instrument is there that you can apply internationally? And that is the IMO submersible guidelines. So one of my recommendations is they should look at whether you want to mandate the compliance with the IMO submersible guidelines in the SOLAS convention. Then the IMO submersible guidelines are more than 20 years old. So they need to revisit those guidelines and probably update the guidelines, okay? And then when it comes to NAVIC 593, this was tailored towards the Atlantis submersible. So I would recommend revisiting that NAVIC and probably updating the NAVIC. It currently applies to passenger submersibles. So perhaps you can also look at whether you want to apply this to other submersibles. For example, if you have a research submersible or a recreational submersible, do we need to have requirements for those submersibles? Okay. So those are my brief recommendations.
Sir, one follow-up on that. Do you think the Coast Guard should only update the NAVIC, or should we update subchapter T, the small passenger vessel regulations, to adapt to submersibles?
Yes,
in your
absolutely.
opinion?
I think subchapter T should be updated, but that's a long process, yeah. So it's much quicker to update the NAVIC, and then, but absolutely, I think the long-term goal should be that subchapter T be updated to address passenger submersibles. The other interesting thing is, if you're under 100 gross tons, you are referred to subchapter T. If you're over 100 gross tons, you go to subchapter H. Neither of these subchapters have any requirements for submersibles.
And sir, the reason I ask that is sometimes we rely on the class
Yes.
standards and other standards, incorporate those into the regulations. Would that be the course that you're recommending in this?
Yes, I would absolutely recommend looking at class society rules because they are updated annually. Yeah? So we have industry-based committees, members of the industry. We have Coast Guard representatives from the U.S. Navy, giving us input as we develop these rules. So it's absolutely valuable to refer to class society rules, going forward, because these are the most updated set of requirements you'll find anywhere.
Thank you, sir.
Absolutely.
Mr. Thomas, you are now released as a witness at this Marine Board. Thank you for your time and cooperation and expertise on this matter. If I need to reach you for further information, I will contact you through Mr. White.
Absolutely. Thank you. Thank you.
I'm sorry. And if you have any questions, you can contact our recorder, Lieutenant Steele.
Absolutely. Thank you so much.
Thank you. The hearing will now recess and reconvene at 1:35.